All right, come on in, sit down, and it's time to talk about hypersonics. Here's your special tool. No one has slides? Okay, that's good. Hey. Okay, this next panel is unusual because no one has slides. So you're not going to have to worry about pointing the pointer at the right place. So hypersonics, before I read my prepared stuff that Jim takes a lot of time to put together for me and then I ignore. But anyway, when I had a real job a few years ago, my company sent me off to look at some hypersonic wind tunnel facilities in a couple of places, or places that were trying to do high performance wind tunnels. Because they had an idea that maybe they wanted to get into that world of operating that kind of thing and managing that kind of thing. And then went off and did that and looked at it. And back then there was not a lot of interest in it. And we found that we didn't think we could make a profit with it. There was not that much of a customer base for it. So we walked away from it. Now in the past 8 months to 14 months, we've had the Chinese come in and say that, yeah, we've got hypersonic missiles. We've had the Russians come in and say, well, we've got hypersonic missiles that you can't touch, and all of your missile defenses and all of your aircraft defenses and all your shipboard defenses will be totally immune, that they'll be immune to any of those defenses. So now we've got a big interest developing again in the United States in hypersonics. So we're going to talk about some of that, some of the hypersonics. And our moderator today is Dr. Mark Lewis. He's director of the IDA Science and Technology Policy Institute. And I had not heard of this institute before, but it's a federally funded research and development center where he leads more than 40 researchers providing analysis of national and international science and technology issues. So, sir.
Thank you. Thank you very much. So in keeping with the theme of the previous panel and our luncheon speaker, I'm happy to report that our panel has a combined total of, I think, 0 hours of spaceflight. Nonetheless, it is the dream panel to talk about the subject at hand, which is hypersonics. And let me start out by echoing the comments. The late George Molnar often said that hypersonics is the future and always will be. But I think it's fair to say that in the current climate, hypersonics is very much here and now. And through the efforts and the encouragement of a number of notable national leaders, including former NASA Administrator Mike Griffin, who's now Undersecretary of Defense for Research and Engineering, hypersonics has once again assumed significance within our national research portfolio. Mike has, in fact, declared hypersonics as the #1 S&T priority for the Department of Defense, and in large measure driven by not only developments in the field, advances in the field, but also the challenges that are being posed by other nations. So to discuss the field of hypersonics, and with maybe a special focus on NASA's role in hypersonics, we have 3 distinguished panel members who I'll introduce in alphabetical order. To my immediate right is Professor Rodney Bowersox. Rodney is the head and the Ford Motor Company Distinguished Professor in the Department of Aerospace Engineering at Texas A&M. Rodney is also the director of the Aerothermal Chemistry and Hypersonics Laboratory, extraordinarily well known for his work on hypersonic boundary layer, looking at surface roughness effects, jet interaction effects, one of our intellectual leaders in the field. Rodney's degrees are bachelor's, master's, and PhD, all from Virginia Tech, before coming to Texas A&M. He served as a faculty member first at the Air Force Institute of Technology and then at the University of Alabama. So Rodney, thanks for joining us. To Rodney's immediate right is Dr. Ravi Chona. Ravi is the Senior Scientist for Structural Integrity in the Aerospace Systems Directorate at the Air Force Research Laboratory. And in that position, he is charged as the senior-most research leader for ensuring that the Air Force has the science technology base required to address the most pressing needs in essentially understanding the coupling of fluids and structures in the high-speed flight realm. Ravi oversees, among other things, a laboratory with some of the nation's most unique capabilities in being able to test acoustic and thermal loads on hypersonic structures. He's been at the Air Force Research Lab since 2003. He spent 16 years on the faculty at Texas A&M, so that's a theme. And his bachelor's, master's, and PhDs are all from the place where I used to work at the University of Maryland, although in mechanical engineering, not aerospace engineering, thus proving no one is perfect.
Or somebody smart.
Or somebody smart, yes. And then to Ravi's right, we're also pleased to be joined today by Jay Dreyer, who is the Deputy Associate Administrator for Programs and the Aeronautics Research Mission Director at NASA headquarters. And in that position, his role is to translate ARM's research portfolio into programs that address actionable needs. And I think that's NASA speak for, Jay actually runs aeronautics for NASA, but we don't tell the AA that. Extraordinarily well known within the field. And Jay has been one, I think, the staunchest advocates for research in high-speed flow in NASA. Prior to joining NASA, Jay did technical support to DARPA. He had a long and distinguished career in the U.S. Navy. He was a submariner, specialized in unmanned systems, and in fact oversaw a research work that uncovered the wreckage of the USS Yorktown and the lost submarine Thresher. Jay's degrees are from the Naval Academy and a master's degree from MIT. Thus proving some people are perfect, by the way. All right. Let me start out with a few words, perhaps a bit of historical perspective before I turn the floor over to our panel members. Hypersonics is not a new field. We've been flying hypersonic objects since the late 1940s, since we put sounding rockets on the top of captured V-2 rockets and flew them out in the desert. Of course, NASA had and its precursor, the NACA, had a long and distinguished role in developing the field of hypersonics. The very concepts for reentry heat shields came out of work that was primarily done at what is now the NASA Ames Research Center, work led by Harvey Allen and Al Eggers that defined the geometry for most of the heat shields that we use today for hypersonic reentry from space back into Earth, back to Earth, or planetary entry for our planetary probes. In modern parlance, though, when we talk about hypersonics, we're mostly talking about vehicles that are designed to spend lots of time in the atmosphere. That means slender geometries, low drag geometries, high lift configurations, and often we're talking about concepts that are powered by engines that can operate in our atmosphere, particularly supersonic combustion ramjets. The Scramjet engine had its origins at what became NASA Glenn. In the late 1950s, two researchers by the name of Weber and McKay, working at the NACA Lewis Flight Propulsion Laboratory, no connection, by the way, began the thought experiment. They knew at the time that a conventional ramjet engine had a limit, a performance limit. Once you got to Mach numbers that were of about above 4 or so, they knew that ramjets stopped working. And they understood one of the problems that ramjets faced was when air comes into the engine, it slows down, and that means that it became hot, exchanging kinetic energy for thermal energy. And at some point, the temperature of the gas coming into the engine becomes so hot, you can no longer burn fuel in that engine. And so they began a thought experiment, which was, what if we never slowed the air inside the engine? The air comes in the front of the engine and continues to move through the engine at high speed. And thus the concept of the scramjet was born. Weber and McKay worked out some of the fundamentals of how that engine would operate and what it would mean for a hypersonic vehicle operating in the atmosphere. And 46 years later, NASA proved that their work was sound when it flew the X-43, once at Mach 7 and again at Mach 10. So again, NASA had a tremendous role in that. The Air Force Research Lab followed that up in 2010 and program that ran until 2013 with its X-51 program, but building very much on the legacy of the work that NASA did on X-43, with many of the technical experts on X-43 advising and interacting with the team that flew X-51. So I think it's especially appropriate that we convene at this Glenn Symposium to talk about hypersonics. Now, as was mentioned, we've kind of gone through some boom and bust cycles in the field. If you plot out funding and programmatic history, the field has about a 15-year periodicity. But yet, I would declare that this time it actually truly is different, and it's different for several reasons. One, because we have flown hardware through the efforts of NASA, through the efforts of the Air Force, through the efforts of other partners, both in industry and work in academia. We've shown that what was once the realm of laboratory research is now practical, achievable hardware. And then two, cycling back to that point, we're in a world where we're being challenged. We have other nations, Russia and China, that have made it clear that they're investing heavily in the field. They're enthusiastic about pursuing hypersonic technologies, and if they do, it has profound implications for the way the United States will posture itself for future conflict. So with that, I'm going to ask our panel members to say a few opening words each, and then we will open the floor for questions, comments, and discussion. So Jay, if you'd like to start off.
Thank you very much. It really is an honor to speak at a symposium such as this, but I must reflect just real quick, just sitting during the last panel, I couldn't help but remember it was about maybe 8 or 9 years ago, we were doing a fundamental aeronautics meeting just a few blocks from here in a hotel where it was, and part of that we asked for 2 keynote speakers, and we're like, wow, we got Joe Engel, an X-15 pilot, and then Mark Lewis, the chief scientist of the Air Force at the time. And I still remember, Mark, your comment standing up there of, thanks a lot for putting me right behind the X-15 pilot in between lunch. And now, after coming after a panel of 5 distinguished astronauts, I know exactly how you felt.
Yeah, that's right.
But all kidding aside, it really is an honor to be here. And talking about hypersonics and from a NASA perspective, we really can look at it in multiple dimensions. I mean, for one thing, it's an inherent part of us just doing our mission when we talk about leaving or returning through Earth's atmosphere or landing on another planet. We talked about hypersonic deceleration on Mars, for example. But really the focus of where the Aeronautics Research Mission Directorate is working is on that air breathing problem that Mark alluded to beforehand. And I think he did an excellent job of laying out some of the history of where NASA has been working in this field for decades to lay some of the groundwork that we're seeing start to come to fruition in flight, especially through what our partners in the DoD are accomplishing. So that begs the question, well, what's next? And from a NASA perspective, while we continue to support the efforts of our DoD colleagues, we're really looking toward that next step in how do we open this up to either further DoD or military applications and also civilian applications for hypersonics. So we're talking about reusability. And so you see a greater focus in the NASA portfolio to start looking at some of those challenges associated with reusability. So we're working on areas like turbine-based combined cycle propulsion. How can we take off and land with a turbine engine but transition to a scramjet for high-speed flight? It's not as simple as just turning one on and the other off. There's a very complex series of managing the flow that needs to occur in that transition, and much of that work is occurring here at the Glenn Research Center that's not going to design a point system, but it's going to generate the knowledge that allows us to develop a whole suite or field of systems with reusable propulsion. Along with that, we're also doing a lot of work into better understanding the analytical capabilities that we need to design the vehicles in general, because the margins associated with hypersonics are so tight. Significant drag, significant thrust, how do you make sure that you can manage and understand the differences between that? We're talking about things like uncertainty quantification across the whole design of the vehicle. So we've got a concerted effort in that area as well. But there's other things that we're also looking into, some of the aerothermal challenges. Things like boundary layer transition have been an issue for decades. They're still not solved problems. We need to understand those if we're really going to get to practical reusable flight. And then we also can talk about the challenges of things like high temperature materials, another thing where NASA has significant expertise. And then finally, one area that we also work that I'd like to comment on, I think that sometimes goes unsung or unnoticed, is in the diagnostic capability that goes along with this. I mean, we talk about and often have a focus on some of the big flight experiments or what we're doing in some of these wind tunnels. But it's more than just the hardware that we're putting in. What are we learning from this? What are the data we're trying to extract from that experiment so that we actually come away with answering questions? And in order to do that, we have to understand things like high temperature sensing in a very complex and a very harsh environment. And a lot of work that NASA does is in this area to help us answer these questions. And sometimes we tend to overlook that or just take it for granted, but it in itself is a significant challenge. And so those of you that listened to Bob Pierce talk yesterday, he talked a little bit about sort of how we do this, this research in partnership with our friends in the DoD. And I like to describe it as that symbiotic relationship where they're taking steps in hardware in both complex ground experiments and in flight to learn and mature and ultimately field systems. What we're doing is providing some of that fundamental knowledge that helps make that successful. And at the same time, we're leveraging all the work that's done there to help inform things like the uncertainty quantification work that we're doing, so that we are building the tools that will help design the next generation of vehicles moving forward. But more important, to kind of how does NASA do this, it really boils down to, I would argue, our people and our facilities. And I list them in that order because truly I believe that the most important asset that NASA brings to the table is the people that we have. The experts that have been, again, working some of this in some cases for decades to learn and understand that. But it's also not a one or the other. It really is the combination of two. And I think if you looked at things like the testing that we did with X-51 that was done at the 8-foot high-temperature tunnel in Langley, people who were really in the know would say it wasn't just that NASA had smart people or NASA had the right facility. We had the combination that really made it work as we were going through that experiment and helping our partners in the DoD take those next steps. So that's why I'd really like to come back to and end with what we mean by the people, because in order for NASA to have smart people, we need to start seeding that next generation. And I would say it's more than just NASA. It's the nation needs smart people working in hypersonics. And so this is another area where we are collaborating. We're working together to do it. And I just want to use one example of that. Fairly recently, the Air Force Office of Scientific Research, or AFOSR, was releasing broad agency announcements seeking university work in the area of hypersonics. We worked with them to say, as part of that, why don't you come to the NASA facilities to actually run some of the experiments? So now we have one of these, really what I would describe as a win-win situation, where you have students that are able to perform experiments in facilities that they probably never would have dreamed of in the university environment, working hand-in-hand with NASA researchers on data that's going to benefit the entire community. And so it's a good example, I think, of us working together to help develop that next generation, because that is really going to be critical as we move forward. So in a nutshell, that's a quick overview of how we're working at NASA in the era of hypersonics.
Thank you very much. Robbie?
Okay. So this panel has an unusual challenge because with our late start and lunch scheduled for noon, and two former academics and one current academic, how do you take three 50-minute pieces and condense them down into one, right? So Mark is the one that's going to have to wield the whip on that. But on a serious note, I'd like to pick up on something that Jay said. If we are going to make progress in hypersonics, and we are going to make the go high, go fast, and do it again and again with the same platform, i.e., basically become the Southwest Airlines of high-speed flight, it is going to take the entire community. The DoD is not going to do it on its own. NASA is not going to do it on its own. Academia is certainly not going to be able to do it on its own, and nor is industry going to be able to do it. It's going to take a very concerted, integrated effort. And I am delighted to be able to tell you that from where I sit, namely in the high-speed structures arena for the Air Force, that community has formed and has coalesced and has come together and is working actively and making huge amounts of progress that when I came to work for the Air Force Research Lab in 2003, I would never have believed we could have attained in the time that has gone by. And it's taken a lot of effort by a lot of people, many of whom never even get the credit. So that is something that I'm delighted is happening. Now, being a structures guy, of course, I'd like to talk about the most important part of any air vehicle, namely the stuff that has to go there, come back, and do it again and again, right? So it's kind of like our human body. We replace a few parts here and there. We can do repairs and so forth. But at the end of the day, once you're a full-grown adult, you pretty much die with the same skeleton that was formed as you grew into adulthood. And that's kind of the story with the structure of any air vehicle. So the challenge that we have, I think, from the structures perspective, is not that we don't know how to fly at high speed, okay, and how to field structures that can survive some duration of high-speed flight. The challenge is to optimize those structures in a safe manner. And I have always said that what you want is you want the minimal mass fraction for the structure, because that is what maximizes your fuel, that's what maximizes your payload, that's what maximizes your range, which are the things you really care about in the end. But you need to be able to do it with high confidence, Jay's comment about uncertainty quantification, because we don't have 100 years of experience flying in and out of that flight regime. We only have isolated data points even after all these years. And you need to be, what you're trying to do is reduce that margin between what you need the structure to be able to do and what you believe the structure is capable of doing. You want to reduce that margin down as tight as possible. Now, that necessarily leads you into a challenge area because it requires that you operate at the interfaces. Now, let me explain what I mean by that. So you're all familiar with the fact that particularly in high-speed flight or any aerodynamic loading situation, you basically have the pressures associated with the flow field, okay? And that translates into, in the high-speed case, some rather intense heating. And that heat, of course, results in temperature changes on the surface, i.e. the outer molar line. And then, of course, that migrates into the structure itself. But the part that we are not taking into account or don't always think about naturally is that thermal loads and mechanical loads differ dramatically in one respect, okay? Because when it comes to thermal loads, the structure wants to relieve those thermal loads by responding to the temperature change. If you raise the temperature several hundred degrees, the instinct is to expand, i.e. you get large thermal strains, but you try to minimize the thermal stresses associated with that temperature load, okay? That's fine if you have an isolated panel sitting on a tabletop with lots of lubricant under it and you shine a heat lamp on it. But when you're part of an air vehicle structure, there is a minor problem because if I'm the panel that is going to try to expand, okay, or wants more room, it's like being in the middle seat of one of these regional jets, right? You got these people on either side of you. They ain't gonna let you go anywhere. So what do, right? You need to deform, you need to change dimension, but you cannot do it in the in plane. So you do it out of plane. You either bow out into the flow or you bow away from the flow. That's how you accommodate the length change that you need to get. Well, now I've got this high-speed Mach 4, 5, 6, 7, pick your favorite number, flow going over this surface. If I start to see the outer molar line deforming into the flow or away from the flow, don't you think that's going to change the flow field a little bit? Yeah? So I've got this very tightly integrated problem now because the driving force is coming from the flow, the structure is responding and deforming in response to that, in particular in response to the temperature change, which in turn changes the flow field, which in turn means that the temperatures and the heat transfer, et cetera, is going to change. And if really nasty things start happening, I might trigger shocks and so forth that can land further aft of where this is all happening. And then, of course, we can get all kinds of spikes and transients and so on and so forth. So one of my colleagues at Texas A&M, Aaron Cohen, that some of you may remember from his days at Johnson and as the director of the Space Shuttle program, always used to say that depending on your perspective, when you live at the interfaces, it's a very dangerous place because it's inhabited by both God and the devil. Okay? And never a truer word was spoken. I never quite understood what he was talking about until I came to work for the Air Force and I was handed this challenge of trying to make high-speed structures a reality. So we have to do what we traditionally don't do in engineering. we cannot decouple the disciplines, okay? So you've got the aero side, you've got the structure side, they're coming together, they're tightly integrated. And oh, by the way, just in case you didn't have enough problems, you've invariably got turbulent flow taking place. So in addition to this mean aerodynamic pressure that you got to deal with, you've now got this fluctuating broadband random vibration from the turbulence that's riding on top of that. And now you've got to somehow figure out what that is doing. So you need long time records, whether computational model, whether experimental investigations, whatever. And these things all have to come together, and that's what defines the loads that your structure has to be able to carry, okay? Once you get those loads correctly figured out, then you have to go pay attention to how the material that you made this thing from is going to respond to that combination of loads. So let me give you an example. What happens if you do uniphysics and you have a multiphysics problem? Say, okay, I need high temperature capability, right? So I'm going to go with something like a CMC. Well, what's one of the characteristics of any ceramic-based material solution? It's inherently brittle. Now I go put vibratory loads on top of a brittle structure. How do you think that's going to respond? Okay? So I may have given myself temperature capability, but I just ramped down my ability to handle this constant fatigue problem that I have from the vibratory loads. What am I talking about here is the fact that this structure is going to constantly evolve because the material it's fabricated from is going to constantly evolve. Evolve is a polite word. The truth is it's going to degrade, okay? So, and by the way, what does that mean in the 50th minute of flight? Will that structure respond in the same way to the applied loads that it responded to in the 5th minute of flight, even if those load sets are identical? The answer is no, because those 45 minutes of flight that have intervened, the material is no longer in the same condition that it was at minute 50 as it was at minute 5. And the same thing is true whether you're talking flight 37 versus flight 3. So again, you've got to take this very integrated approach, and from a material standpoint, you don't have a single failure state to live with. It's not going to be governed by buckling. It's not going to be governed by yielding. It's not going to be governed by fatigue. It's going to be governed by things like thermomechanical creep fatigue with some amount probably of nonlinear material deformation, permanent deformation as well. We don't think that way because 99% of what we do doesn't require us to think that way. Hypersonics is the exception. You have to take that holistic, integrated view of things, and you have to do it in an area where you really don't know a lot. So I like to tell people, you know what's going to happen is as we go further and further and further towards making routine hypersonic flight a reality, we better be prepared to instrument those vehicles in such a way that every flight becomes another flight test and we can gather information and we can build up that database that we must have. In the meantime, when we're trying to get there, we are faced with the challenge that our ground test facilities, regardless of how good they may be, regardless of how world unique they may be, like the ones Mark talked about, the combined environment facilities that we have at the Air Force Research Lab in Dayton, they just represent small points in a very large operating envelope. So we're constantly looking for new ways to be able to do things. And as we gather as a community, as we exchange information, I mean, I had a delightful conversation with Dave Stringer last night, which hopefully is going to lead to some increased interactions between what he's doing at Plumbrook with some of the high-speed facilities there and what we are trying to do from the Air Force end in trying to do practical work in structures. We've got to create the community. How are we doing that at the Air Force? We are working closely with NASA Okay, you alluded to the combined cycle work. There's a very active program between some of my colleagues at Wright-Patt and the folks here at Glenn. It's all about the control and the inlet and how do you make all those things come together in the right way. There's mentoring taking place with more senior folks working actively with younger people. Actually, I learned recently that that mentoring approach that has been developed between NASA and the Air Force for this work on the combined cycle engine development has been recognized as being a best practice. And if I'm not wrong, I think it's Johns Hopkins Applied Physics Lab that is picking up on that. My own folks at AFRL, we have a very active academic collaboration, formal collaborative center and other partners. Mark is on our advisory board and knows all about that. And it's about creating not just the knowledge, but creating the people. An S&T base, again, going back to what Jay said, is people and knowledge. Without one, you cannot, without both of them, you cannot do what you need to do.
And Ravi, that's a great lead-in
To what Rodney
for
is
Rodney.
going to talk about. Thank you.
All right, so first, I want to say that I'm humbled to be here at the John Glenn, this first symposium. He's one of my heroes, just to put that out there. He has a couple of quotes that I really like. One is, anyone who doesn't want to be first doesn't belong in the program. I think I agree with that. And he also would quote on legacy versus legacy. I think he preferred the legacy side of things. So I'm going to zoom out a little bit and talk about aerospace education first, and then I'll focus back down on hypersonics a little bit here. So there are about 75 aerospace programs across the country, and the enthusiasm right now for aerospace, I think in my career, it's at an all-time high. Over the last 7 years or so, our enrollments in our department have nearly doubled in terms of interest in aerospace. The country's graduating between 4,000 and 5,000 aerospace engineers a year. They're interested in space. We talked a lot about space. We had astronauts here. Our students are pushing us to have stronger programs in space, and in fact, we've hired a couple of astronauts to help us do this. Bonnie Dunbar is one of them, and Greg Shamatoff is another one. And Bonnie likes to remind me every day that we talk about hypersonics, that she's the only one that's actually flown hypersonically in our department, her and Greg. So this is true. So I think this is a great time for aerospace, not only in hypersonics. The national push in hypersonics is real. Our students are coming in. We're getting calls all the time about wanting to work in hypersonics. And the national push in space and space exploration is equally important to our students. And Mark mentioned scramjets and wave riders, and he mentioned the role of NASA Glenn, but I'm going to also mention the role of academia. In fact, Fred Billig at the University of Maryland, working with the Applied Physics Lab, was a big player. I think he owns one of the patents, or used to own one of the patents on scramjets. And Mark, being very modest, was also one of the leaders in wave riders back when those were being developed. And the X-51 is a wave rider that proofed a scramjet. So academia has had an important role in hypersonics since the beginning. Hypersonics, as Dr. Chono was describing, is a scientifically rich problem, so academic folks are interested in it. It's the applications are very cool. Re-entry, everyone's seen the movies and they've seen the photos of the capsules re-entering and the air is basically exploding around the aircraft and it's on fire behind it. What student doesn't get excited about that? And so it's easy to attract students to the field, I think. The job market is fantastic right now. It's hard to keep students in graduate school, so it is a great time. It is inherently interdisciplinary, and it's an interesting problem. I've been working in this problem with chemists. I've been working on hypersonics, but my partner in crime has been from the chemistry department for the last 15 years on this. And I want to zoom back out a little bit and talk about Bonnie Dunbar one more time, because you also mentioned Joe Engel. Joe Engel and I met back in the early 2000s, and then most recently, maybe 2-3 years ago, he visited A&M to give one of our Molina lectures, which is one of our named lectureships, and he did fly the X-15. So we went out to the lab and we printed the X-15. And there was a famous experiment where the scramjet model on the bottom of the X-15 fell off. Mark knows what I'm talking about. It was a structures problem, so you've got work to do.
Yeah.
We're still trying to solve this problem, but it was a shock-shock interaction that created a hotspot that torched through the pylon that was holding this on. So we did a 3D print of this with the scramjet on there, and we duplicated in the wind tunnel the shock-shock interaction, and we put the hotspot right where it was on that. And Joe didn't fly that flight, by the way. But he was so psyched because he was like, that's exactly where it burned off. It was right there, because we had IR live thermography going during the wind tunnel experiment. So I got a photo of Joe Engel, headphones on, goggles, watching the experiment, just getting excited. So it was a great day in the labs. And he signed that X-15 model, and so I have it in my office. That's probably very valuable right now. But anyway, and in this past week, in fact, getting back to hypersonics and academic interest in hypersonics, I was just at the joint AFOSR, ONR, and Hypersonic Vehicle Systems Institute program review, still going on today. Today's the last day of it. And they're basically funding basic research in academia. And there was at least 100 presentations over the week on basic studies, and these studies are supporting graduate students in the workforce of tomorrow to help solve these problems. And the topic areas at this particular program review included Aero Thermodynamics. I'm sorry, there was a little bit of structures going on there.
Small amount.
Small amount, yep. He mentioned transition to turbulence. That is an incredibly important problem. The heat transfer rates can go up by a factor of 5 when you have between laminar and turbulent flow. And the overshoot in between can be even worse. And so the last thing you want to do is fly transitional. You either want to be turbulent or laminar, but not in between. Not high temperature, non-equilibrium gas dynamics, the glowing. Bonnie likes to talk about what it looked like when she would fly back into the Earth's atmosphere. They have photos of the glow, which is very interesting. And then, of course, the last topic that we talked about there are the fluid structure interactions, which is shock boundary interactions, creating a lot of these acoustic loading problems that the Air Force and NASA is very interested in, because these are the things that will vibrate the panels off of the vehicle. And so there's a lot of very fundamental research being supported through the DoD and NASA at universities and building the workforce and also building the knowledge base to help develop future systems. So academia does have a big role to play. I think I'll stop there.
Thank you. So now we've actually already been accumulating online questions, and so if it's okay, I've got the list, and let me start out. So some of the questions are drilling down deep, and some are kind of broad, but the most popular question is, when do you think hypersonics will be used for commercial use instead of just military? Jay, I'm going to defer to you on that one.
That's a good question. And part of it is, what do we mean by commercial use? Because there's a number of applications where hypersonics could find its way into the civilian markets. We talk about things like, that's been on the drawing board for a number of years, is access to space. And I'll remind folks, it's not just about low-cost access to space, but the flexibility that a reusable air-breathing hypersonic system might entail. And perhaps something like that would start with smaller payloads at first. So an application there may be much more practical than, say, flying humans on a reusable, say, on a point-to-point type of mission. It really is hard to pick a number and say, well, we're going to see it by this date or that. It's clearly not going to happen, I would say, within the next 10 years or so. I mean, there's a number of steps that have to take place before that. But I do like to remind people, if we don't take those steps, those initial ones that perhaps have primarily a military application, then we're not going to get to the civilian applications when it comes to hypersonics. So to me, it's a little bit of not getting too far ahead of ourselves. We know what the next things that we need to do, and if we take our eye off that ball, we can pretty much guarantee we're not going to get to those longer. Whether it's 2040, 2050, it really won't matter at that point. So I would say I would hate to pick a number, but I really say the focus should be on the what we do next.
So if I may, I remember in 2010, I was president of AIAA. We were rolling out a new green energy initiative. We did a press conference in D.C. And one of the reporters asked me, he said, well, Dr. Lewis, you're best known for your work in hypersonics. You're talking about green energy and impact on the environment. And what do you think the connection is between hypersonics and the environment? And without thinking and ignoring all that media training the Air Force gave me, I said, if we ever get to the point where hypersonic vehicles are damaging the environment, I'll be delighted. And then, and then I realized, oh, that's not the best quote to rent. So, but yeah. All right, we've got another question, and that is, are our competitors smarter than us, or are they lying about our capabilities? Robbie, you want to take the first stab at that one?
I don't think.
Mike, just speak. Yeah. It's pressure activated.
Okay, I'll try without it. Go into my lecturing voice. I don't think necessarily that our competition is smarter. I think what our competition has is a will and a willingness to invest and to invest in a consistent manner. That is where I think the difference comes in.
Yep, agree. And we did their homework for them in many cases.
Well, of course.
Yeah.
But that's because we have, as a nation, have never kept science and technology developments at the fundamental level have never been shielded.
Very good. Anyone else want to jump in on that? Or? That's a good answer. Okay, here's one. And Ronnie, I'm going to defer to you in this. Could you explain what aerothermochemistry is?
Sure. This is a term coined by Theodore von Karman back in the 50s, actually. And it's the combination of aerodynamics and fluid mechanics with chemistry and combustion. So he coined this term, this phrase, because it's important in the aerospace field for propulsion and external aerodynamics. So aerothermochemistry is what that means.
Very good. Next question. We've talked a lot about materials, but is there any research yet on how flying hypersonically might affect the human body?
So I don't know if I can directly comment on that point, but it actually ties into maybe the first question on the commercial applications of space. So one thing we have done is some very high level, and again, not specific vehicle designs or things like this, but we've done systems analysis work on what would, say, a point-to-point vehicle look like. And some of the challenges get exactly to that point. What type of accelerations do you have? But even things like, what type of environment are we going to have in the cabin? It's not going to be practical if everyone's going to have to wear a spacesuit when we fly this. But think about not just a small cabin like we see in a capsule, but a large, like what you would see in a small regional jet or even a business jet. How are you going to do the air quality there, the temperature controls and things like this? It's a non-trivial problem when you talk about flying through an atmosphere where your outside temperatures are in the thousands of degrees type of thing. So I wouldn't say specifically what it does to the human body. We at least haven't been looking at that yet from a NASA perspective. I think more of that learning maybe come out of what we have out of things like shuttle experience, because we are flying hypersonically in some of these cases in space applications. So I think that learning is probably the best source that we'll have to drive toward that. But it's not anything that we're focused on right now.
Okay. Let me see also if there are any questions from the live audience. I haven't seen any hands up. Question over here. All right.
So potentially one uniquely NASA application for hypersonics would be maybe in the area of like aerogravity assist for exploration of the outer planets. With this resurgence in the interest in the DoD for hypersonics, is there any thought of trying to leverage some of that technology development for that potentially uniquely NASA application?
I'm not going to answer for NASA and the Air Force, but I will mention that there is a history of collaboration between the Air Force and NASA on very much along these lines. In fact, if we rewind, I don't know, half a dozen years ago, there was a National Center for Hypersonics Transition and Transition which was jointly funded by AFOSR and NASA. There was also a materials version, hypersonic materials version, and there was also a hypersonic propulsion version, all at the same time. And this was a $30 million investment over about 5 years in terms of, and so the NASA applications were, of course, more exploration, and the Air Force applications were more military focused. So there is indeed a history of that.
So if I can, aerogravity assist is one of my favorite subjects. So using aerodynamic forces to enhance a gravity assist maneuver. There are two gentlemen at JPL who worked on it for many years, Jim Randolph and Angus McRonald, and they showed you could do some amazing things. The idea is essentially you augment the energy you get from a gravity assist by diving into the atmosphere and using aerodynamic forces to hold you there. The challenge is you wind up diving into planetary atmospheres at horrendously high Mach numbers. So McRonald and Randolph came up with one trajectory that would get you from Earth to Venus to Mars to Pluto in just a couple of years. You know, basically shave a decade off the transit time. By the way, lends itself to great acronyms because the Venus-Mars transit they called a Vaga-Maga because it was, aerogravity assist AGA. At any rate, their first maneuver into the atmosphere of Venus though would occur at close to Mach 70. So Ravi, how's that for an aerothermodynamic challenge? Yeah. But the good news is the vehicle only has to survive for a little bit. So, yeah. Let's see. We have a question online about the work that is underway between the United States and the Australians at Woomera. Anyone like to address what's going on there?
So a lot of that effort has been in understanding laminar to turbulent transitions, when they occur, and more importantly, being able to predict when they will occur. We're very good in engineering, we're very good at post-dicting and saying why something happened. But the key really to expanding the future is to be able to predict with a high level of confidence. So the folks that came up with the idea of using those sounding rockets to do very controlled experiments, it was a great concept. And I think that whole US-Australia cooperation on that has been just phenomenal in terms of the amount of knowledge that has been gained and the cost at which it has been gained and the speed, i.e. not how fast it's flown, but the relatively short duration of time between flights, between experiments that we've been able to achieve. So it's a great success.
Yeah, and I'll comment on that as well. And it's more than just the collaboration that we're doing right now with the Australians. It really spans, I mean, probably longer than a decade of where we've done things like some of these flight experiments on sounding rockets. It's primarily been driven as an Air Force-led activity that developed the international partnership, but then domestically reached back right away from the initiation of the program to NASA. So NASA's been intricately involved in this along the way, has developed some of the specific experiments that have flown over the years going through this, but I would agree with the sentiment. It's been a good example of a successful partnership, but also a good example of how we're taking the right kind of learning approach and looking at early applications of flight in this regime. Instead of just saying, well, we can do it computationally or do it in the tunnels, there's some things we just have to learn by flying, and I think there was some good focus and some good learning that's come out of these that helps build that fundamental knowledge base that's going to help us take those next steps. So this has been one of those key successes.
And I think we'd also all agree that the Australians have been phenomenal partners in this arena. Ronnie, you in?
I did. I think so. We're talking about for those of you in the audience, we're talking about the HIFIRE program, which is this Hypersonic International Flight Research Program. But it's continuing, and there are going to be some similar flights supported out of AFOSR that are university-led. In fact, we're leading one, and APL is leading the other one. The APL one will be flown out of by the DLR, but the one that A&M is working will be flown out of Wallops by NASA. So these flight tests are happening not only in Australia but around the world and also in the U.S. I just want to point that out.
Excellent. Let me see if there are more questions from the audience, because I know we had some hands up.
I have one, sir. I think it's a structures question, but your mentioning of the sitting in the middle seat.
Right.
I had an experience a couple weeks ago where I was thankful for my Bose noise-canceling headset when I was stuck in the middle seat for about 9 hours. as the day the jet went off the runway at Newark, and so I was grateful for the noise canceling. I'm wondering, when you were talking about the vibratory loads in the structure, is there anything mechanically we can do to cancel out that type of vibration actively, like piezoelectrics or something like that, that we can actively induce into the airframe to cancel out those vibratory loads?
So the place where those vibratory loads are going to impact you the most is on the outer moor line, on the outer skin. And the difficulty with any sort of active control mechanisms is the temperatures that you have to deal with. Piezos, for example, will let you go up to a couple of 100 degrees Fahrenheit at most, maybe up into about 250 degrees Fahrenheit. And even in relatively benign flight conditions like Mach 5-ish continuous flight regime, you're probably looking at 700 to 800 degrees Fahrenheit at a minimum on that outer moor line. And that's away from the leading edges. So those are the challenges that you run into, unfortunately.
Let me take a question from online, and Rodney, I'm gonna address this one to you. So, as a community, how do we talk openly enough to excite and engage the next generation of hypersonics workforce while still protecting the information as appropriate?
That's actually a very complicated
I know.
question. But I will speak a little in generalities about this. As I mentioned earlier, the applications are cool. And if you're talking, I mean, if we mentioned the commercial applications of hypersonic, Boeing is pushing a Mach 5 airplane. And you show this to a student and say, this could be the future airplane that you may help design. That's really a great sell to bring students into the program. NASA does a wonderful job. The outreach that NASA does through social media, my favorite things to look at on Facebook are photos of asteroids and planets and everything else that NASA's doing. So NASA's really helping us out with this, and I think going after undergraduate students, I mean, they're coming into the programs now asking about hypersonics. I mean, so the word is out that hypersonics is important. I don't think we really have to discuss with students at any level things that would be sensitive to get them excited about aerospace engineering or get them excited about hypersonics. So I don't think it's as tough a problem as it may sound. Now, keeping students in graduate school and getting them to go get PhDs and doing things like this is a little bit more difficult. And there's where we have to lean on folks like the Air Force, and we can send students to internships. And we can send students to NASA with internships or into industry with internships, and they come back really excited about these fields. And so I don't think I'm giving a good answer to this question because it's very complex, but I do think that the applications are exciting enough that they are drawing students. Like I said, our enrollments, they're at all-time high. We're one of the most selected departments in the college. I mean, we're turning away, our average incoming GPAs are higher than they've ever been, and so we're really getting great students interested in aerospace engineering right now. So I don't see it as a huge challenge.
Anyone else want to?
Yeah, go ahead, Al.
I was going to say that I think there are some lessons we can learn. One of those lessons we can learn in that regard is looking at what DOE and in particular Sandia National Labs did some years ago, where they formed research centers at universities on problems that, or challenges, I should say, that you might say, well, why is Sandia worried about that? So the one at University of Utah was on fire research and how fires propagate through a building and so forth. The one at University of Illinois had to do with modeling what goes on in liquid rocket motor combustion processes. Why did they pick those particular problems? They picked those particular problems because they were looking for new ways of doing the computations that were involved with some of the things that Sandia is interested in, but which they cannot talk about outside their fence. So they chose these challenges which involve differential equations that are coupled and that have the same form as the problems that they're really interested in, and said, okay, if you can develop new ways of attacking these families of mathematical problems, then that will be useful to us. The other thing that you can do, and which we are actively doing at AFRL, at least in my group, is that we work very hard to sanitize the information that we are gathering so that we can put data sets out there, so that we can provide benchmark problems that are realistic in terms of both geometries and configurations and loading conditions and the response of the structure and the material to those. It takes a lot of effort.
Jay, you had.
Yeah, so one comment I'd have on that is I think we should also attack the problem head on and not just say try to mitigate it, but actually say how do we turn this into an opportunity? And what I mean by that is, listen to Dr. Bowersox. The drive is there from setting out the challenges. The students are coming. So we don't necessarily need to shield them from this issue, but why not start educating them early on what we're talking about of how we release or how we disseminate some of this scientific information. It's cut and dry if it's classified information. That's the easy part to some degree. It's the learning that we're doing at the fundamental level that for decades we're just used to publishing. And you're in a university environment where we're used to publishing things. And this gets back to, I think, your point, Dr. Chona, on hey, sometimes hypersonics is the exception rather than the rule. There's an exception here, and perhaps we need to tell students, you're not just going to go out in the open and publish this, but there are forms where it is appropriate to do so. So they're learning that from an early age. Before they're even entering the workforce at NASA, at the DoD, or within an industry, they have that as part of the building of the knowledge that they're doing. And then I think it's up to us in the government role to set those venues and to accept students, bring them in early rather than saying, well, this is just for DoD and industry, but are we not starting to engage academia more so that we understand the problem collectively rather than treating it as this is one part and the universities are just going to publish openly.
Very good. And by the way, as a programming note, our timekeeping overlords have told me we can run a little bit long, but not too long because we all need to hear from Charlie. I'm going to jump the online list a little bit because there's a question here that I really like, and I'm going to ask all three of our panel members to address it. What application for hypersonics excites you the most? Wow.
It's one of those, it's kind of like, and it's not the same thing, but it's almost like when you ask, well, which is your kids is your favorite, type of thing. I know this is maybe going to sound like a cop-out type of answer, but what excites me about it is it's almost not the application. It's, whether, because, I come from a DoD background, I'll admit, I'm excited about something that's going to give us a technical superiority that, maintains an advantage that we have. I think just in the near term, I see that practical application. So I'll say maybe I do resonate toward that. But really what I think I'm most excited about is how this is bringing government together and how it's exciting young people. We keep coming back to this workforce development piece of it, and seeing that element of it is actually what impresses me the most. Like when we're bringing people in to study in the Langley Aerothermal Lab, excited about it and want to make a difference for the country. It's kind of that mindset that actually excites me more about this field than the specific applications itself.
Rami?
So I know that my Texas accent may have misled you, but actually I am originally from India, and every time I take a trip there, I go through a door-to-door journey that spans about 30 hours. So the idea of being able to get there in a few, I will happily settle for single digits, is personally very exciting. From a professional standpoint, I think that hypersonics is the key to maintaining and providing the national security needs that the United States has to have going forward. Because the ability to go out and touch someone wherever they are very shortly after you decide that you want to go out and touch them is just, it cannot be surpassed in terms of the impact on national security.
Okay, so I agree with both of those, but you mentioned aerobraking. All right. When I was an undergraduate, back when I had hair, on all of that. I was doing my senior design project, and I opted to do the space transfer, orbit transfer project, and we were doing Holman transfers, and that was like watching grass grow. So then they said, literally, so then they said, well, we need someone to do the aerobraking part of this project. And I didn't even know what aerobraking meant, but I said, I don't want to do Holman transfers anymore, so I'll do aerobraking. And so I started to work on this problem as a senior, not having a lot of aerothermal chemistry background back then. But my senior design professor put me in contact with some folks at NASA Langley who were very, very gracious in providing information on how these processes worked, and the notion that molecules will go across the shock wave and literally explode and fly around this vehicle and create a plasma, all of it was just incredibly intoxicating. I just couldn't stop thinking about it, and I'm still working that problem many years later. And so for me, it was the physics associated with that problem that really hooked me, and I knew I was in the right field, and we've been working it ever since. But the applications, again, going from this planet to another planet, skipping through atmospheres, that's an amazing idea. Screaming across this planet using a supersonic combustion ramjet, which is another amazing idea where you have to inject fuel into a device. It's basically a box with some stuff in there to make things mix, but you have to inject it and mix it and combust it efficiently, all in about a millisecond. That's 1/1000th of a second. All of these things have to happen. That's an incredibly hard, scientifically, engineering, technology. There's nothing easy about that problem. So this is what really gets us exciting. And so in our lab, we get excited when we see things for the first time. And they're small things, right? The students will make a measurement. We'll see something in a boundary layer, and we go, wow, we've never seen that before. And we're high-fiving because we're the first people to ever see that. And so it's really kind of cool, even though it's not we're not building an airplane, but we're studying some of the physics behind it. And so this is what gets me excited about hypersonics.
So if I can exercise moderator's discretion and also answer the question. So I agree with everything that's been said. Anyone who's ever been on an airplane flying to Australia understands the value if we could only do that at hypersonic speeds. But for me, actually, the most exciting application is the most distant one, which is access to space. And think about what it takes to launch. We just had a panel of shuttle astronauts, and think about what it took to launch the space shuttle. A phenomenal machine, but a standing army of thousands of engineers and technicians would have to prepare that vehicle 3-4 months in advance of a flight. Now compare that to an airplane taking off from Cleveland Airport. The airplane pulls up to the gate, they get the passengers off, get the bags off, they clean the toilets sometimes. They used to put food on board, they don't bother doing that anymore. 15 minutes later, that airplane is ready to take off again. If we could build vehicles that could fly into the space regime with more of an airplane-like model and less of a rocket model, think about what that would mean for space access. Now, it's a very long way off. Maybe my great-grandchildren will get to see that. But I think that, for me, is the ultimate brass ring. Let me see if I've been told we've got a couple more minutes. Are there any questions from the audience?
Hi, folks. So this is a comment to the human physiology stuff that Jay Dreyer talked about. We do have a body of knowledge. We just have to go back and look for it. X-15, 199 flights, Mach 6.7. Would be great to see where the flight surgeon records are on the people that flew the X-15. We have the A-12, YF-12, SR-71 body of data, both CIA and Air Force and NASA, that would be extremely useful to retrieve. As we saw out of the Apollo data that was recently mined in the last 2 years, we found out that we knew that lunar dust was abrasive corrosive. We suspected we knew it had electrical potential. What we didn't know was the 10-meter high effect only works during the day. When you're in darkness, it settles back down. So there's any number of things we can do, and these make great grant types of things. For Ravi, this makes great 711th Human Performance Wing type of research to say, where do we get leading edge work? Well, we actually have some, so thanks.
Excellent. Very good. And if I You know, the gentleman who holds the record for hypersonic flight in a powered vehicle in the atmosphere was Pete Knight. He set that record in X-15 about 51 years ago. And until recently, his son, Steve Knight, was congressman from California. Then his district included Edwards Air Force Base. And Steve used to say that his father would be really upset. He passed away a number of years ago, but he'd be really upset to know that he still holds that speed record. So let me see if we have probably time for one last question. Make it a good one. Wow, if not, let me pick my favorite from the online, which is, and it was addressed to those of us who have been in academia or currently academia, but I'm going to open it up. Jay, would you fly in a hypersonic vehicle that one of your students, and I'll extend it to colleagues, has designed?
Absolutely.
Okay.
Sure, if I blessed them with a degree, why not?
Right.
Exactly my answer, right there.
Okay, excellent. Thank you. Let me thank our panel. It's been a fascinating discussion. And also let me thank our audience for being very participatory, and thank you for your questions.
Excellent. Dr. Lewis, thank you so much. Really appreciate it. Thank you. All right. And with that, we're going to break for our lunch with our guest speaker, Charlie Bolton. As we do, thank you again to all of our sponsors for this event. We seriously could not do this without you, so we appreciate it very much. I'm not sure if I got the trivia answer to the previous question put up there. So Zero Gravity Research Facility was designated a historical landmark in 1985. And if you don't know about that, it's amazing. It's a 470-foot deep well right there at Glenn. It's very cool. Anyway, so this piece of trivia now, most important. We were founded in, and we'll get you the answer when you come back. So lunch will be outside, grab it, come back in, grab your seats, and then we'll get started with the speaker. Thanks, everybody.